Good evening. Welcome to the QCIS channel. We're on this channel, you get a daily dose of science, technology, engineering, and math. My name is Leon Jones, and today's topic, or let's say this evening's topic, I want to talk about estimating earthwork. Now, in construction, there is a lot of backfill, there's a lot of borrowed soil, there's a lot of excavation going on. Now, what we have to understand is excavation and backfill, they're part of quantities when we deal with a construction contract. And earthwork is very, very costly because you have to deal with labor, materials, and of course, the excavation and the backfill of soil material. So basically, when we talk about excavation, there are methods that we can calculate how we get the quantities of excavation. Now, when it comes to units, there are two units that we can use. Excavation comes in volume. So we're going to use cubic feet or cubic yards. So again, earthwork can be estimated by using the average in area method for smaller projects by averaging two cross-sectional areas and multiplying by the distance between them. Now, generally you have stations. And then you also have the grid cell method for medium-sized projects, and that's by dividing the site into cells and summing the volume differences. And the cross-section method for larger projects is basically executed by taking frequent cross sections. So today we have a lot of software that can do all that work for you. So for the most accurate results, average methods involve what we call DTM. That's digital terrain modeling, and that's generated from site surveys processed by specialized software like AutoCAD Civil 3D or Trimble Business Center. Now, what I'm going to show you in this PowerPoint is how we estimate earthwork. And this is definitely important. And I'm going to tell you why I'm doing this video as well, because this is, if you're going to be taking this civil FE exam, you are going to see a couple of problems in the survey section where you're going to have to estimate software. You're going to have to use the trapezoidal method, the average in method. And if you don't understand the concepts, figuring out the quantities can be very, very, very difficult. Now, estimating earthwork, again, it includes, I just mentioned it earlier, excavation, grading. That's moving earth to change elevation. Now, when we talk about grading, we're talking about cuts and fills. Now, a cut is when you are going to take soil from a certain grade. Fill is when you're going to backfill, and then you're going to have temporary shoring. Now, shoring could come with steel. It could come with I-beams, and you have wood planks in between each I-beam. And again, I just mentioned it earlier, backfill or fill, that's adding earth to a raised grade. That's known as a fill. And moving earth or taking away earth, that's called cut. Then you're going to increase density by compaction. And generally, compaction is also measured with a nuclear density gauge, or you can still use the sand cone method, although the sand cone method takes a longer time, but it is very accurate. And then, what if it's bad soil? You're going to have to dispose it. So all of that's going to be utilized when that item is estimated for a contract. Then we have our productivity factors, job conditions, material type, water level and moisture content, job size, length of haul, haul road condition. And we're talking about accessibility and load restrictions. Now, normally a truck can basically carry 73,200 pounds. Anything over that, and you are an inspector, you're going to have to write that up because that's out of spec. That's right, 73,200. And generally, trucks can get weighed at weigh stations. I know at the plants they have weigh stations, but generally, most of your trucks are right around 20 tons. So you want to put 20 tons of material, that's okay. 2,000 pounds equals a ton. So again, when we have productivity factors, we have management conditions, equipment conditions and maintenance practices, skills of workforce and management, planning, supervision, and coordination of the work. And we have the job efficiency factors for earth moving operations. So again, we have management conditions. We have excellent, good, fair, and poor. And these are the numbers that you are going to utilize to find out what you have out there. Then, again, units of measure. So you have a cubic yard, bank, loose, or compacted. So for bank, it's a BCY. That's called a bank cubic yard. That is material in its natural state before disturbance. That's known as in situ or in place. And then you have your LCY. That is loose cubic yards. That's material that has been compacted or disturbed or loaded. And then you have your CCY. That's your compacted cubic yard. That is material after. Now, generally, when you look at this diagram, you have 1 cubic yard in natural condition. And then after excavating, it's 1.25 cubic yards. So for the most part, in your natural condition, you have in situ or in place. After you excavate it, you're basically going to have loose yards. And then once you bring in a bulldozer or any type of other piece of equipment, such as a roller, then your density is going to go down, or your cubic yards, or your volume. Let's say the volume is going to go down after it is compacted. So this is why you have to pay close enough attention to what is in the contract, what you're going to be paying for. And then when we deal with volume, again, V sub B, bank cubic yards, density, bank, pounds per bank cubic yards. And we have loose, V subscript 1, loose cubic yards, LCY, density, loose pounds per loose cubic yards. And then we have compacted, V sub C, compacted cubic yards, density C, pounds per cubic yard. C stands for compacted cubic yards. Then you're definitely, take notes. This is definitely on the FB exam. We deal with bank volume, load factor, and swell. Now, an increase in volume when it's excavated, that's known as swell. So swell is always done in percent. So basically, you're going to have your bank density divided by your loose density minus 1 times 100, because you are looking at percent swell. And you know, when soil gets wet, it could swell as well. Then you're going to have your load factor. That's your loose density versus your bank density. Or we can say loose density divided by bank density. Then we have our bank volume, which is loose volume times load factor. So even when you do soil, you might think that the contractor's just playing in dirt. No, you have to be able to move dirt around. You have to look at your contours because you have existing contours and you're going to have new contours. This is where your grade stakes come into play. You have to learn how to read the grade stakes. Now, shrinkage, that's another one. It's when soil basically decreases in volume when it is compacted. And then you're going to have your 1 minus your bank density divided by your compacted density times 100. Your shrinkage factor is 1 minus shrinkage. And then your compacted volume equals bank volume times shrinkage factor. Then you have your approximate material characteristics. Approximate material characteristics. Now, this is what you're going to use. Exact values will vary with grain size, moisture content, compaction, etc. Test to determine exact values for specific soils. So these are some of your specific soils. And as I mentioned earlier, I mentioned load factor. I mentioned swell, bank, pounds per cubic yard, loose, also pounds per cubic yards. You have your clay, it's wet and dry. Then you have your clay and gravel, wet and dry. Then you have dry earth, moist earth, wet gravel, dry sand, sand and gravel that's dry, and you have sand and gravel that's wet. Now, you have your typical soil volume conversion factors, and this is what you're going to use. So if I have bank and I want to take my loose, I'm going to convert loose to compacted by using these factors. When I get my whiteboard up, I will go over some of these problems. Now, if you are in grad school and you're a geotechnical engineer, you're going to use a lot of this information as well. And this is also, believe it or not, going to be on your PE in the geotechnical section. So you're going to have to know how soil works. It's more than just digging. It's more than just backfill. Then, estimating earthwork for trenches and foundations. Well, you have 2 feet, you have your angle of repose. And you have your approximate angle of repose, and that's for sloping sides of excavation. So you have your original ground line, and then you have your well-rounded loose sand, 2 to 1, 26 degrees, 1.5 to 1, 33 degrees. That's your compacted sharp sand, 1 to 1, 45 degrees. That is your recommended slope. In fact, a lot of your slopes are 1 to 1. We do recommend 1 to 1 because it's 45 degrees. And we also have 1.5 to 1 at 63 degrees. That is your compacted angular gravel. Now, calculating earthwork quantities. I just mentioned a couple of them. So the familiar ones are the average in method, or the average area, or the end area method. And then we have the contour line grid method. Now, for the end area method, it's used in sites where length is much greater than width. So when we use the end area method, we're going to take cross sections at regular intervals, typically at 100-foot intervals. We're going to calculate the cross section in areas. And then we're going to look at the volume between the sections. It's the volume of earthwork between sections. And it's basically obtained by taking the average of end areas at each station in square feet multiplied by the distance between sections in feet and dividing by 27 to obtain the volume in cubic yards. Now, let me put that in layman terms. When we take the distance is the length. You need 3 components to get volume. So what we're doing at each station, we already have square feet. So I could have 27 square feet at station 100. And then I'm going to move the station 200. So I already have my length of 100 feet. So what's going to happen is I'm going to have another area. Now, the area could be trapezoidal, where you're going to have to take your 2 bases, divide them by 2, and multiply them by your height, or 1/2 base times height. That's how you get your area. But basically, what you're doing, you already have your areas at the stations, and then you're basically length times width times height. So basically, volume is area times length divided by 27. So you have your project site showing 100-foot stations. So you have 500 feet. So each station is 100 feet. So then you have your contours, 78, 80, 82, 84, 86, and 88. And basically have 300 feet. So you look at your project cross sections. And you have cross section AA. So you come up with an area. And notice it's a triangle. Area is triangle. So you probably have 193 times 1.8. Now, how did I get that 1.8? I want to tell you how I got that 1.8. That's what people don't know. I got that 1.8 because from 76.7 to 78.5, it's 1.8 feet. And that's from here to here. And then from here to here, it's 193 feet. It's just like here. How did I get 53.5? Well, I have 79.5. And then I have 78.5. That's 1. So right here, this hypotenuse is going to give you your hypotenuse is along the side, or it could be this side, but this is how you get it. I'm going to take the area of these 2 triangles and then multiply it by its length. And this is my first area. And then this is my second area. So if I had 100 feet to the next area, this is where I'm going to get my volume. You're dealing with cross sections. You're dealing with the same thing here. 210 times 1.8. Dealing with the same thing here. Cross sections. And your cross sections are also on your plans as well. Then you have your cumulative earthwork quantities. So you look at it, A minus B. Going to come up with a certain number, 470. This is your cumulative. You're going to add 170. And when they say cumulative, you're going to start right here on the top, add this number, may even subtract. Now, let me tell you something. When you add, you're filling. And when you're subtracting, you're cutting. You just remember that. It's just like here, 672. I'll take 24 away, or I'm going to take this. This is what I got when I excavated here. So you're going to take 672 minus 202 to get 470. That's how they got it. Same way here. You have to understand your math. And this is definitely on the FE exam or the PE exam as well. Then you have and this is a little more complicated. And this is, if you're going to be doing any type of site leveling or parking lots, you're going to use grid size. And grid sizes could go 10 by 10 to 50 by 50. The greater the terrain variance, the smaller the grid. Again, the contour line grid cell method. This can be very complicated, but basically you determine by visual study of the site drawing if the net total will be an import, which is more fill required than cut, or an export that's less fill required than cut, or blend, cut and fill about equal. And then you're to determine the pattern of calculation points of grid size. Then you're going to determine the elevations at each calculation location and the corners of each grid. And then you're going to calculate the cubic yards of cut or fill required in each grid cell. And then you're going to add the individual grid cell quantities together to arrive at the total cut, total fill volume, and the import or volume export yardage that's going to be required for the job. And here's what the grid method looks like. Again, it could be a little complicated. I do know how to do it. And when I get the whiteboard up, I'm definitely going to do it. Now you have to look at what they're giving you. See, all grids are 50 by 50. So each grid, this is a grid right here, 50 by 50. So it's 2,500 square feet. Now these are all of your contour lines, all of your contour lines. And you have to bring the entire site to elevation 90. So this one right here is 90. So what you're going to have to do, you're going to have to bring this up 2 feet. This is going to be fill. This is going to be fill. This is going to be 1 foot, 2 feet. You're already at 90. So that means you're going to have to cut a foot to make it 90, cut 2 feet, cut 3 feet, cut 4 feet. That's how you get that. Because they want it to be almost like a building pad. Thing is at one elevation. Now, propose. Grade the entire site to 90. So just like I told you before, it's 150 by 300. So here, I just mentioned it to you. You need fill over here and you need cut. So assume one grid. Existing contour is 90.50. Proposed is 90. So what are we going to have to do? You already have, if it's in your head, we have to get everything down to 90. So that means we're going to cut. So this is a very simple thing that you have to do. You need to know your grid size. So I already know my grid size. And this is a quick and dirty trick. See, when you're in college, they don't really teach you this information, but you have to understand when you have your map, you got to get everything. I wasn't even taught this in school. I figured this out because some things don't have to be complicated. A lot of people make them complicated. So this is a grid right here. So you have 90 and you have 91. So right here, I don't have to do anything at all. This is my proposed grade right here. This is my proposal. You want 90. This is what I have existing. So because this is existing, this is another elevation, and this is another elevation right here. However, we're looking at the existing contour right now at 90.5, and I want you to pay close attention. Pay close attention to this whole diagram because you have 90 right here. It says you need fill and you need cut. Now, you have to get the length and the width of each grid. So right now, we have the length and the width. So we already know that's 150 times 300. Now, in order to get to 90, we're going to have to cut 0.5. So your 0.5 is basically going to be your depth. This is very, very simple. Very simple. That is your depth. Length times width times height, length times width times depth. And you divide it by 27. Now, let's check it on my calculator. What I'm going to do, I'm going to go ahead. So I already have a grid. Length 150, width 300. Now, I already know my existing contour right now is 90.5. So my proposed contour, I want to get it to 90. So what am I going to have to do? I'm going to have to cut, which means go down a half a foot or 0.5. So my depth is going to be 50. And then I come up with 2,250,000 cubic feet. And then I divide it by 27. And I come up with, they come up with 833 cubic yards. But well, that's when I multiplied it by 50. That's my mistake. It's 150. That's 150 times 300. And I'm basically taking half the area anyway. And I'm multiplying it by 0.5. And then I'm dividing it by 27. And then I come up with 833.33 cubic yards. Now, let's go over it again to show you how I got that. You have the length and the width of the grid right here. You already have your, what we call your proposed contour. That's your proposed elevation. So anything on the left side, you're going to need fill because it's less than 90. Then on the right side, you're going to need to cut it because it's greater than 90. So I'm already given 150 for my length, 300 for my width, and then I'm given my existing contour. So because I'm given an existing contour, I don't have to worry about this 91 until I get to 91. But what I'm going to worry about is this 90.5. That's existing. See, 91 right here, by the way, if you look at it, you would actually need, you want to get it to 91, you need, basically, you're going to add a half a foot. In other words, it's going to be plus, it's going to be 0.5 plus 0.5, which is going to give you 91. And so if you want to get that one, then we're going to take 15, 150, I'm doing some math here, times 300, times 1, and I'm going to divide that by 27. I'm going to come up with a different. In fact, I'm going to come up with 1,666. Why? Because I'm adding a foot. In other words, this 0.5, it's 833. Well, for that half a foot, that's going to double. And this is why it's very expensive when you are dealing with excavation, because I'm going to have to double. But I want to cut this. I want to get it down to 90, and I want to get it down to 90. Say I'm 91. So basically, I want to cut it. That's a cut, not a fill. Fill you're going to add. Cut, we're going to take away a foot. But that's how you do earthwork. Again, another one. Suppose we chose a grid size to be 50 by 50 again. So what are we going to do here? Well, again, you look at the diagram. You have 87.6, 87.6, 88. This should be 88.5, 88.5, and then you're going to add all these together, and then you're going to have 88.08. So you have 90. So what is it going to be? If you want to get it down to 88.8, your change is 1.92. That's a cut. And that's how you do that. And that's basically how you, and this is just an overview, how you do computations with earthwork. And once again, when we talk about earthwork, we have different methods. Again, earthwork can be estimated by using the average in area method for smaller projects, and that's by averaging two cross-sectional areas and multiplying by the distance between them. Then we have the grid cell method for medium-sized projects. It's used by dividing the site into two cells and summing the volume differences. And the cross-section method for larger projects, it's by taking the frequent cross-sections. So basically, for the most accurate results, advanced methods involve digital terrain models generated from detailed site surveys that are processed by specialized software like AutoCAD, Civil 3D, or Trimble Business Center. Now, again, let's talk about conventional methods. And these are simpler, and this is one of my favorite ones. The average end area method is best for smaller projects or when a detailed survey is not practical. Now, how it works. You're basically going to take the volume between two adjacent sections, and that's calculated by their average end areas. And you're going to average their end areas like A1 and A2, and then you're going to multiply by the distance L between them. So V equals A1 plus A2 divided by 2 times L. Then we have the cell block method or the grid cell block method, best for medium-sized projects with regular grids. How it works. It's the project area and you divide it into a grid of cells. The existing and proposed elevations are averaged for the corners of each cell to calculate the volume difference cut or fill, which is then summed up the total volume. And then you have the cross-section method. Again, it's best for large or complex projects like roads where terrain variations are significant. So you have frequent cross sections, basically vertical profiles. They're taken across the site, and then the area of the cross section is calculated, and these areas are then used with other methods, such as the average end area method, to determine the volume. And then, if you are in the computers, there are advanced methods. Now, these methods use technology for greater accuracy and efficiency, DTM, known as digital terrain modeling and 3D modeling, best for accurate visualization and planning for complex projects. How it works? Well, you have a detailed topographical survey, and what that survey has in it, it has all of the features of that topo. So the survey is going to create a digital terrain model, which is a 3D digital representation of the existing ground surface. And that's everything that was surveyed out there, from your trees to your telephone poles, to your road surface or EP, to your sidewalls, to your buildings. And then you have software. The software creates a 3D model of the proposed design, allowing for precise calculation of cut and fill volumes by assessing the differences between the two surfaces. And then also, you have specialized software. It's best for automated and precise volume calculations on any project size. How it works? Well, you have programs like AutoCAD, Civil, 3D. Now, your contractors, this is what they use, your HCSS, Heavy Bid, or your Trimble Business Center. They also use digital terrain modeling and design data to automate the calculation of earthwork quantities by reducing errors and improving efficiency. And Geopack, they have a software too, and you have some of the older software that came out in the early 2000s, and it's ancient now. But when I was in the military, we also used it. So basically, when we deal with any type of earthwork, we use a couple of methods like your average in area method and your grid cell block method, so we can get the quantities, and the quantities are always in volume. Remember, the quantities are always in volume. So when you're an inspector, and you're out there, and a contractor, you have class 1 excavation, class 4 excavation. This is for road, and this is for pipes. Or you have to know how to calculate the amount, because if they put pipe in, they have to fill. Something you need to learn about this. What you do is, if they cut a trench, it's square. You're going to take that whole volume, then you're going to subtract out height. That's what you're going to pay the contractor. Now, the contractor is also going to get paid for the pipe. For the excavation, you have to subtract that pipe in order to get an accurate count of excavation. If you don't, you're going to pay the contractor more excavation than they placed for the pipe. And that's why, as an inspector, and even as an RPR or project supervisor, you need to look at the plans, and you also need to know how to calculate the volume of excavation yourself. And for the FE, it's very important that you know the calculation as well. And for the PE, because if you're going to go into geotechnical engineering, or if you're going to go work for a contractor, or even work for yourself as a contractor, this is where money is made, or this is where money is lost. So basically, this was an overview of calculation, methods of calculating earthwork, estimating a quantity. So what I want everybody to do, if you're taking the FE, PE, check out this video. This is just an overview. It's going to give you the basis, the basics. And when you understand the basics, you can figure out complex problems. But start with the basics. Start with the basics at the basis. Work a few problems, get comfortable, and that'll build your confidence. Because in the end, this is all part of engineering. Engineering is science and math. Actually, engineering now is science, technology, engineering, and math. So, if you want to be a geotechnical engineer, start by taking a soil mechanics course, surveying course. You can get more into the complex information if you go to graduate school. So that completes this topic on methods of estimating earthwork or contracts. If you like what I just presented, please comment, share, and subscribe. And if you are looking for political and social content, check out my main channel, the 411 Talk Zone radio show channel. Now, here's where you can find me. On the 411 Talk Zone radio show channel, you can find me right here on YouTube, find me on X, formerly Twitter, Rumble, and also Truth Social. And for this channel, the QCIS channel, you can find me right here on YouTube, X, formerly Twitter, and LinkedIn. And once again, thank you for viewing this topic on estimation of earthwork quantities for construction right here on the QCIS channel. On this channel, you get a daily dose of science, technology, engineering, and math. Until next time, my name is Leon Jones. I want you all to have a wonderful and gracious evening.